All right, so that's a bit on constant acceleration. Let's have a look here at variable acceleration. Okay. All right, and boxed in there are the basic relationships that we can use. So we got v is ds dt, a is dv dt, and ads is v dv. So once again, there's three equations that you can use. So let's look at a couple examples here. On 133, let's say we got a block and it starts from rest at a time equals 0, and then it moves in a straight line with its velocity described as v is 6t minus 3t squared. T's in seconds. So when the time is 3, let's find the acceleration of the block, displacement of the block, and the distance traveled by the block. Okay. All right, and so let's start having a look at this. All right. Now what we got there is we got v is equal to 6t minus 3t squared, right? Now what we can always do, you can always use calculus. The only thing you can be unsure about is using the constant acceleration equations. You can't do that if you got variable acceleration. It doesn't work. But calculus will always work. Okay. So what we can do then is we could just go ahead and find the acceleration and see what's going on here. So a is dv dt. And we can just take a time derivative of that function there and see what we come up with. And I think what we're going to come up with is 6 minus, is it just 6t? Is that it? Okay. All right. So I'd start by figuring out what the acceleration is. And it's 6 minus 6t. And I'm just doing a simple derivative to get that one figured out. And that's a dt on the bottom. Like I said, I'm having some trouble with my pen right now. So based on that, do we got constant or variable acceleration? Yeah, it's variable, right? Okay, so that's the first thing I want to identify. So that's what I got. Okay. And I want to get that figured out because that will tell me what my choices are, for equations that I could throw at this thing, okay? All right, so I got variable acceleration here. dv dt is 6 minus 6t. When I plug in t equals 3, I come up with negative 12 for the acceleration. So that's the acceleration when the time is 3. So I've got this one figured out already. Now what I've got there is variable acceleration. Okay. Now variable acceleration means I got three equations I can use. V is ds dt, a is dv dt, and ads is v dv. Those are the three I can use. All right, and I know the acceleration. I want to find the displacement next. So which one of those will work? Which one of those will get me the displacement, do you think? I might have to mess around with it some and work with it a little bit to figure it out. But which one of those could I use to get to displacement?
ADS equals VDT.
This one looks kind of tempting. But the problem here on this one is I don't have acceleration as a function of displacement. So I have acceleration as a function of time. I can't just plug that into this one. It won't work because the t won't match the ds, and I can't do anything with it. So that one's out. I use this when I don't have a function of time.
That one would be used for the distance instead.
Right.
It's the change in displacement.
Yeah, right. That would work if acceleration is a function of distance, or displacement actually be the technical term to use. Yeah. All right. So I got to figure out, I got velocity as or acceleration as a function of displacement. What do we do? We want to find the displacement time. Okay, let's see what we can do here, because we've got v as a function of time. If we use this one, we can rearrange it a bit and work with that, I think. So let's work with the one on the left and see what we can do with it. And this is a very typical way to handle dynamics. What we're doing here is we did a derivative and worked our way down that a way to get to the acceleration, but we can also integrate, and that's what we're going to do here. So let's use that left-hand equation, because velocity is a function of time, and see what we can do with it. So here's how I'll work with that. I know that v is 6t minus 3t squared. And I know that ds dt then is v. They're equivalent. That's 6t minus 6t squared, or minus 3t squared, right here. So I'm just taking the v and converting it into ds dt there. Now, even though these really aren't algebraic variables, you can work with them as though they are. So if the change in displacement with respect to the change in time is 6t minus 3t squared, that means the change in displacement is 6t minus 3t squared times dt, the change in time. Okay? Now that's a differential relationship. Those are two instantaneous things that are happening that are equal. The change in displacement at a given instant is 6t minus 3t squared times the change in time at that given instant. Now what I want to do is get that back to the variables. I don't want to work with ds and dt. I want to work with s and t. Okay? So what I can do to accomplish that is I can integrate. That'll get me from a ds back to an s, and from a dt back to a form of t. All right? Because what integrals are, they're adding things up over a given interval. So if I add up a whole bunch of ds's over a given interval, I'll get back to what s is. And if I add up this function times dt over a given interval, I'll get a function of t, all right? And that's what I want, so I can relate these together. Now the important thing here is I've got to add them up over intervals that correspond. The interval I have to use to add up the ds has to correspond to the interval that I use for the dt. I can't just throw an indefinite integral at this. I got to put limits in here that tie them together, so to speak, okay? So here's how I approach this. What's my starting time on this thing? It's 0, right? What's s when the time is 0? It's 0, yeah. So I want zeros in the bottom, because when the time is 0, the displacement is 0. So I set it up that way. Now so that's how I'm getting those, the bottom limits. Now this isn't arbitrary, because when the time is 0, the displacement is 0. If I had some number line here, when the time was 0, the displacement was 2, I'd have to use 2 and 0 as my limit, see? They got to match. They have to represent things that are happening at the same instant, okay? That way they'll correspond, and you'll be adding up over the same interval. This is what you want to do with these integrals. Now for my top limits, I always just put letters in here, s and t. I can always plug the numbers in later, and sometimes I might want to do more with the integrals. So I don't put letters or numbers on the top. On this one I could put a 3 in for t, right? Because that's what I want to know the information for. But if I do that, I don't have a functional relationship between s and t, and that's really what I want. I can always plug the numbers in later. So rather than using 0 and 3 for the time integral limits, I'm just going to use 0 and t. I'll plug the 3 in later. That's how I approach these, okay? All right. So in red there, I've kind of got some notes on this. So the limits of integration should be matching values. Okay. So that's why I'm using 0 and 0 on the bottom, because when t is 0, s is 0. On the top, I'm just putting in s and t. It allows me to get a functional relationship that I can do more with if I need to. I can always plug in the numbers later and get the numerical answer. But if I plug letters in there, I'll get a nice equation that I can work with, as opposed to just an answer for a particular value. All right? That's why I'm doing it this way. All right, so I'm plugging in 0 and s and 0 and t. And you should understand what I'm writing there, and if you're not confident you do, write that stuff down, because these are, when I write these explanations down, it's because they're things that require explanation that people need to remember. So, remember to do that when you're listening to your instructors go on and say a bunch of stuff. Write down the stuff in your notes between the steps and the equations. You ever had that happen when you look at the dang equation that you wrote down in class and you go, well, how the heck did that happen? How'd they do that? See, what you want to do is write down the explanation they're giving you, if you got time, as you're writing down the equation. Sometimes you got to remember more than just the equation. Okay? So the limits on this stuff are important. They should match, and I leave those top ones as letters, because I just might need to do more with that relationship. So that's why I'm doing that, okay? So we okay with that? Doing all right? All right, so when I plug in 0 and 0 on the bottom and s and t on the top, when I integrate ds, I get s. Plug in the limits, I get s minus 0, which is just s. Plug in 0 and t and integrate the one on the right. 6t integrates out as 3t squared, and 3 minus 3t squared integrates out as t cubed. So I get, when the integral is 3t squared minus t cubed, plug in the limits, and I get 3t squared minus t cubed is s. Now I might be doing a little overkill by plugging in all these zeros, but I do it just so you have a nice template to work with. So if your limits aren't 0, this is how you'd handle it. You'd plug in that stuff on the right, okay? So what we got now is we went from this calculus relationship, ds dt is 6t minus 3t squared. We got that down now to s is 3t squared minus t cubed. See, we got a relationship now between s, displacement, and t, which is time. Okay. Now, if I want to know what the displacement is when t is 3, I can just plug 3 in for t, and I can find s. I mean, that's all I got to do now. Okay. We good with that? Any questions? Okay. So when I plug in 3, look what happens here. Plug in 3, I get 3 times 3 squared minus 3 cubed. That works out to be 0. What happened? What's the explanation for that? Why didn't that block go anywhere? It's got an initial velocity.
Is it negative acceleration going the other way?
Yeah, what it did, it went out, it had an acceleration going the opposite direction, and it came back. Okay? Displacement's 0, but the distance isn't. It's like me coming here. I start at home, I drive here, then I drive back. Okay? That's what happened. So that's why s is 0. And a tip-off on that was that acceleration was negative. That initial velocity's to the right, or soon is when you start plugging times in there. But the acceleration's to the left, okay? Now, if we want to figure out the distance this thing travels, let's see if we can do that. But the displacement's 0. It starts and ends at the same place. Now, if we want to figure out what the distance is, what can we figure out about this place out here? Because the distance is going to be twice the displacement from here to here. What's a known thing we know about here that we could use to figure this out, how far out it goes? There you go. Yeah, velocity 0 here because it's turning around. Okay? So the displacement is 0, but the distance isn't. And to help us find the distance, let's use the fact that when it turns around, the velocity is 0. Okay. So what I'm getting at here with some of this stuff is we do the calculations, but understand what they mean too, right? I mean, these different things have different meanings to them. All right. All right, so that's V is 0 out there, okay? And here you see a good reason to plug letters into the top of that relationship instead of numbers. Because what I got a relationship that V was 6t minus 3t squared. And I'm going to do more with that now. I'm not just going to plug 3 in for t. Now I'm going to plug 0 in for V and solve for the time. One root is t equals 0. The other one is t equals 2. So it looks like that thing turns around when t is 2. Okay. And what I'm doing there, I'm solving t I'm getting 3t squared is 6t. I can look at it and tell that one solution to that is t equals 0. I mean, that's a quadratic equation is what it is, but I don't want to do the b squared, negative b plus or minus b squared stuff. I just want to solve it. So I know this is true. 3t squared is 6t, so t equals 0 is a root. Once I found that that's a root, I can eliminate it from my other possibilities, which means I can divide through by t now. If t is 0, I can't divide through, but if I've solved for it, found it is 0, and eliminated that from the rest of the possibilities now, I can go ahead and assume that t is not 0 for the second solution. So I can divide through by t, get 3t is 6, so t is 2. So at t equals 2, the velocity is 0 and the thing's turning around. That's what we got out of that. So what I can do now is plug t equals 2 into the displacement relationship and get the displacement, then double it, and that'll be the distance. Okay. You all okay with that? All right, so I just plug in 2 for t because s is 3t squared minus t cubed. Plug in t equals 2. I get s is 4 meters. So the distance is twice that. It's 8 meters. Okay. Yeah, of course.
What if we don't have something that's as well behaved? How could we calculate the total distance?
Don't have something that,
Yeah.
that doesn't have a nice clean function.
Yeah.
Yeah, that's something, in dynamics books, we get nice clean functions, and that's what we get in school. When you start working, you don't.
Mm-hmm.
So what you have to come up with then are graphical ways of solving these things. You'd probably, if you were doing this for real, you'd probably have some sort of sensors you were working with. You could tell, when it turned around and came back.
Yeah. So
So if you have the nice clean functions, you can't integrate, but then you can do things like graphical integration if you've got data for the whole path of the thing. So I guess in absence of a nice clean function, you need more data, and then you use graphical techniques to integrate. I guess that'd be what comes to my mind to answer that. Yeah. Okay. And, when I worked a bit, I didn't ever do calculus when I worked, but I used ideas from calculus to solve stuff out. I had a pump station I was working on once, and I had to size what's called the wet well, and I just threw it on a spreadsheet and kind of modeled how much water would be coming in versus what's coming out, and how big the well that held the water had to be based on some different scenarios. So that's my experience working. You don't do this kind of stuff quite near so much, really, but you use the concepts in a spreadsheet or Scilab or MATLAB or something like that and knock through things. Okay. All right. Other questions? Are we doing all right with that? So the key ideas there are you can split the differentials and integrate. That's done a lot here in dynamics. What's going on right there? Going from there down to here is kind of an important step, because you can integrate the second thing I underlined there and get back to the variables. Okay, so that's one key idea there. Another one there is plugging in the limits and making sure that your limits match. 0 and 0 on the bottom, S and I use letters on the top. That just works a little better, I think. It gives you more options down the road. Okay. So those are kind of some of the key things we did on that one, all right? All right. Well, we look at one other here. Let's say we got a spring on a block. It's going to push that block, and we've got the velocity of the blocks going to the right. Looks like the spring's going to push back to the left there. Now the spring exerts a force that's a function of its length, so it's a linear spring. So the acceleration then, which would be proportional to the force that's exerted, will be linear also. So it's negative. In this case, our coefficient is 1.2 times S. So S is the spring constant there. Or actually, no, S is the amount of displacement in the spring, sorry. It's negative because we're moving to the right, but the spring pushes it to the left. So that thing has an acceleration to the right, but an acceleration to the left. And let's find the speed of the block when S is 0.9 meters and the maximum displacement of the spring. Okay. All right. So we got constant acceleration or variable on this one. Yeah, variable, right? Because A is 1.2 S negative. Now S is not seconds. S is displacement. Watch that. That's that can be one of those little errors that people make sometimes because we're used to S meaning seconds, but in this case, S means displacement. Okay? That's how S is defined. So it's variable. So if it's variable, we're going to use those calculus relationships there. Which one are we going to use? Have a look at what you got. That's what you got. We want to find the speed of the block. Third? Yeah, it's the third one. That's going to involve speed, velocity there. And also notice that A is a function of displacement. Okay? You can't just take this relationship and cram it into there. It's just not going to work because you don't have A as a function of time or velocity. A is a function of displacement. So you can't do that. You just can't do anything with it once you've plugged it in. These functional relationships work because they're related to each other. They're related to certain things. A is given as a function of S, the displacement of the spring. We can plug it into that third equation. It's set up to accommodate that. Okay? You can't just force it into the second. You can't do anything with it once you got it. Okay? We good with that? Okay, so why don't you plug it in there, and let's see what's going to happen here next. Okay, we're going to plug it in. So A ds is v dv. A is negative 1.2 s ds. And then we equate that to v dv. Okay? So negative 1.2 SDS is V dV. Okay, because A is negative 1.2 S. Now, we got to get away from the ds and the dv. And the standard way you do that is you integrate, okay? And this is standard stuff. You do this, this is how you do this stuff, okay? So get used to this. To get out of those differentials, you got to integrate them. Add them up over an interval, and then instead of a ds, it becomes an s, essentially. Okay, and that's how that goes. All right, now, so we're going to integrate it. Now, why don't you put the limits in there? What are the limits going to be? Just take a couple minutes and see if you can do that. Maybe just a couple minutes. We're a bit short of time here, apparently. That clock there is quite a bit off. Okay. So when we start integrating, what's S? Zero. What's V?
2.
It's 2, okay? So watch it. You can't just do antiderivatives on this stuff. You got to account for your starting conditions. When S is 0, V is 2. Those go in as your lower limits, okay? And just pay attention to that, because you can't just, people sometimes get a little sloppy and they just do antiderivatives and just equate them. You can't do that because S is not 0 when V is 0. Those don't equate. S is 0 when V is 2, okay? So that's how this one has to be. And then the top limits are just S. And again, my pen isn't working very well, but that's an S and a V, okay? So the limits of integration are 0 in S and 2 in V. And it's shown right here. I mean, there's going to be some place in the problem where it's stated directly. So when S is 0, V is 2, okay? So just be in the habit of watching that. Top limits, just use letters. You can always plug the numbers in later. And then integrate it out. And these things usually take a little bit of time to integrate. The nice thing here is you don't got to know anything about velocity. V dv, you just integrate it. It's v squared over 2. And then s, negative 1.2s, integrates out as negative 0.6s squared. And then you just plug in the limits. And work it on down, and I get to this place here. So negative 1.2s squared is v squared minus 4. Okay. So that got us out of the ds and dv stuff. We wanted to get out of that, and then we watch our limits carefully. They're 0 and 2. It's right there in the sketch. And then we walk it on down there, plug in the limits. And what did I do there? I just multiplied through by 2 to clear the 1/2 is what I did. So the negative 0.6s squared times 2 is negative 1.2s squared. And then the 2 times 1/2, that just cancels. So I get v squared over 4 down below there, okay? So I get down to negative 1.2s squared is v squared minus 4. All right, and I want to know what's the velocity when s is 0.9, so I can just plug in 0.9 in for s, and I can solve for v, okay? All right. And And I went ahead, I worked with the algebra a bit more. I got v squared is 1.2 s squared plus 4. I just brought the 4 over. Then I plugged in 0.9, and I can solve for v. And actually that's plus or minus because, you know, the way springs work, you'll get a velocity going that way, and then if that spring, if energy is conserved, you'll get it going back the other way too. So it's really plus or minus technically. But right when it hits that 0.9 the first time, it's 1.74. Okay, and then short of time, we'll just finish this up. I'll get you some homework here to be working on. Got it here. All right, we good on that so far? So remember to keep getting your packet if you don't have it yet. We'll go over. You guys both got the packet. I got the packet. Okay. Oh, you do.
And or the do you have the assignment list and due date online somewhere?
Yeah, it's in Moodle, the assignment list. Let's finish this thing up though. I thought you were copying this down, so I was gonna pass this out, but here, let's just. Okay, so we get to the fact that V is 1.74. Are we good with that? Uh-oh, battery's running low. We're in trouble. Will we make it? Okay, maximum spring displacement is the other thing we wanted to know. V is 0 when that occurs, right? So you can just go ahead and solve for S using that, and it's 1.83 meters per second. So we often have to interpret the problem statement and get it incorporated into the equation is something that we often have to do. All right, get this plugged in. All right, so I'll get you 3 problems to do, and these will be due Monday, so if you got questions on them, we'll cover them on Friday. So what do we got? We got 111, we've got 122, and 123. I'll write them down here. 111, 122, and 123. Okay, and these are due Monday. Okay, and I've got copies of them here. Although, you know, I would have the packet good to go by Friday. I think that'd probably be the best way to go. But if you want a copy of these guys,
Sure.
yeah, these will be Monday. We'll cover them on Friday. If you've got questions, we'll take You doing all right? So we'll cover this stuff Friday. Remember to get that packet. I'll stop the recording, then I'll get back to that one slide for those of you that want it. But okay.